We will conduct an experiment where the surface a liquid boils on affects how fast it boils. Different surfaces have different roughness, geometry, and ways that interact with the liquid, and all of that changes how easily the liquid can nucleate, meaning how easily bubbles can form and detach. Nucleation is just as important for boiling as temperature because the liquid can't actually transition to vapor without places to form bubbles. So, if a surface has more nucleation sites, then the liquid should start boiling sooner, which means its temperature is rising faster. This idea that more nucleation sites make the liquid heat up and reach its boiling point faster. This is captured in this equation, Regime 3 boiling heat flux equation. Heat flux is how fast the thermal energy enters the liquid per unit area. The main part relevance is here shown on the screen. So, if the CFS is smaller, the heat flux is larger, meaning energy enters the liquid faster and its temperature increases more quickly. Point is, more nucleation sites means the temperature rises faster, which means the liquid reaches its boiling point sooner. We will be conducting this experiment in 4 different trials. 2 of them will be done on the stovetop and 2 of them will be done with the microwave. This will also use 2 different weighing measurements of boiling chips. Starting with our stovetop, we are able to show that the principles by heating water to its boiling point in a pot on the stove and changing the surface the water is boiling on has the effect of increasing the time of boiling. We ran 3 trials, one with no boiling chips, one with 3.03 grams of boiling chips, and one with 6.06 grams of boiling chips, which is double the amount from the previous trial. Each trial used the same pot, the same burner setting, and the same amount of water. As the water heated up, we measured the temperature every 30 seconds. We expected that adding more chips will make the water boil faster. We are able to conduct this experiment by placing calcium carbonate boiling chips into the water. These boiling chips are small, porous, solid pieces that have several tiny cavities where bubbles can easily form. The results lined up with what we expected. Shown in the graph, the trial with no chips heated the slowest. It reached a boiling temperature at the latest time. And the slope of our T time over temperature curve is the least steep. With the trial of the smaller amount of boiling chips, it reached its boiling point sooner and has the steepest slope. And the trial with the most boiling chips heated the fastest and had the most steepest slope compared to all 3. Now we are testing the same principle in the microwave. Each trial is similar to the ones before. One with no boiling chips, one with 3.03 grams, and 1.6.06 grams. We use the same glass cup and the same microwave wattage and half a cup of water for each of these trials, heating in 10-second intervals. But microwaves behave differently. The glass cup is smoother than the metal pot, so it provides far fewer nucleation sites. And instead of heating through conduction and convection like on the stove, the microwave heats the water directly through radiation, so the water does not move around much. The combination of a smooth surface and little mixing means the water can superheat, heat up to a boiling temperature without actually boiling. When reaching superheating, putting an object into the water will result in bubbles appearing around it. That's because inserting the object introduced nucleation sites. It gave the water a surface to nucleate on, and movement of the water also helped the nucleation. Since the water was hot enough to boil, bubbles began to form. When reaching superheated, the water will bubble when an object is placed in it. Because the object introduces nucleation sites, unlike the stovetop trials, the microwave temperature versus time graphs didn't show much difference between the amounts of boiling chips. A potential reason is that we didn't add enough chips on top of the smooth glass surface and still water not providing many nucleation sites. Both parts of the demonstration showed that the material the liquid boils in affects how the liquid boils. because it influences how easily bubbles can nucleate. For the stovetop, adding boiling chips increased the amount of nucleation sites, which would lower the CFS value and increase heat flux. That made the temperature of the water increase faster. In the microwave, the glass cup provides fewer nucleation sites, and radiation is the main heating mechanism. As a result, changing the amounts of boiling chips did not change the temperature versus time curve as much. But when inserting an object into the hot water, bubbles began to form because we introduced new nucleation sites. These results demonstrate that surface influences the boiling process.